Okay, going through the process that I had just finished on that previous example where you have to divide all the terms by the highest power of x from the denominator is not always necessary. I went ahead and did it just to show you that process because there's going to be some times that you will have to do it. But when you're dealing with a rational function, of course, when you're dealing with a rational function, that means if you look at your numerator and your denominator separately, they both also have to be polynomials, okay? But if that's the situation, then you can actually follow one of these three guidelines and it makes it a lot quicker. And it's just a matter of comparing the degrees of your numerator and your denominator. So as the first one states, if the degree of the numerator is less than the degree of the denominator, then the limit's at 0. If the degree of the numerator is equal to the degree of the denominator, then the limit is the ratio of the leading coefficients. And last, if the degree of the numerator is greater than the degree of your denominator, then the limit does not exist. All right, so I'm going to give you an example of each of these three situations. Okay, so the first one that you see here, you have to, of course, in all three of these situations, you need to determine the degree of your numerator and the degree of your denominator. So the degree of my numerator would be 1, because that x that I have here is understood to be to the first power. So I've got a 1. And then the degree of my denominator is going to be 2. So what you would say is that 1 is less than 2. So going back to the three situations, this would actually fit the first situation because the degree of the numerator is less than the degree of the denominator. So as it states, your limit is going to be 0. So the limit, this is not something you would have to write down, but the limit of this rational function would be x equals 0, or I'm sorry, at 0. So you wouldn't have to go through and do all that division like I did a while ago. Of course, what this also tells you is that you would have a horizontal asymptote at 0. All right, the next situation, the degree of the numerator is 2. The degree of the denominator is also 2. So in this case, you have them equal to each other. So this is the second situation where it says that it's the ratio of the leading coefficients. So the leading coefficient in my numerator is the 2, and the leading coefficient in my denominator is the 3. Of course, when it says that it's the ratio, that means that you're making a fraction. So your limit is at 2/3, or your horizontal asymptote would be at 2/3. Okay, last situation here. The degree of your numerator is 3. The degree of your denominator is 2. So in this case, you have a greater than situation. So that's the third one in which your limit does not exist. Okay, which would mean you would have no horizontal asymptote in that case. So when you have a rational function, that means the numerator is a polynomial, the denominator is a polynomial, then you can use these shortcut rules to help you figure out your limits. Okay, now, relating this to horizontal asymptotes real quick, of course, we just finished looking at those rational functions. And as it states, rational functions approach the same horizontal asymptote to the right and to the left, whereas other functions may approach different horizontal asymptotes to a different horizontal asymptote to the right and to the left. So, going back, and I don't think I pointed this out a while ago. Actually, the first two you noticed that I did was positive infinity, and here I did negative infinity, but yet I was still able to use the rules exactly the same because it's only, as it stated, this is a rational function. It's going to approach exactly the same horizontal asymptote to the left and to the right. So it wouldn't matter whether you did the limit as x approaches infinity or x approaches negative infinity, the result is going to come out to be the same. But if you have some other type of function, you can have different asymptotes. Okay, so you can have more than just one asymptote with some functions, and that's actually what you see on this next example. Okay, so on this one's not considered, I mean, even though it's a fraction, this is not considered to be rational because your denominator is not a polynomial. You've got this square root. All right, so because we're approaching positive infinity, so we're going to define x as being equivalent to square root x, okay? Because we need to look at it in the numerator here as x, but in the denominator when we do our work, we need to look at it as square root x. Okay, you're still going to go through that process where you have to divide everything in the numerator and denominator by the highest power of x. And actually what you're going to do on the top is you're going to divide everything by x. Now remember, these two things are equivalent to each other. So you're going to have the 3x divided by x minus the 2 divided by x. Now on the bottom, you're going to divide the square root by square root x squared. Okay, because like I said, these two things are equivalent, so I'm using just the x up here and I'm using the square root x down here. Now let's go ahead and take care of my numerator here. Of course, here my x's are going to cancel, which would leave me with just a 3. Now, since these are both over square roots, then you're allowed to, just write it as one big square root, and then you'll have the 2x squared divided by x squared plus 1 over x squared. Okay. So doing some more simplifying on the bottom, here the x squareds are going to cancel out, which will leave me with 2, and then I'll have the 1 over x squared. Okay, so now let's go through and let's take the limit of each of these terms individually, just like what we had done earlier. So the limit of 3 is going to be 3. The limit of, as x approaches infinity, of 2 divided by x is going to be 0. Okay, now you're allowed to come underneath your radical here and do the same thing with each of these terms. So the limit of the 2 is going to be 0, and the limit as x approaches, I meant to say 2, I think I said 0. But then the limit as x approaches infinity of 1 over x squared is going to be 0. Again, both of these is that property that I had showed you earlier. So I end up with positive 3 on the top and square root 2 on the bottom, which would mean, of course, again, this is also the location of your horizontal asymptote, okay? Now, this one approached positive infinity, so now let's look and see what's going to happen as you approach negative infinity. Now, in this case, because you're not dealing with a rational function, you're not guaranteed to have the same limit to the left as you are to the right. So in this case, you would have to deal with the fact that x is going to be equivalent to negative square root of x squared. Okay, so going through similar steps that we did just a few minutes ago, I'm going to divide everything on the top by x, but then on the bottom, I'm going to divide by negative square root x squared. Okay, so let's go ahead and do the simplify the top. So here the x is canceled, which just leaves me with 3. And again, I can take this to just one big square root. This would just be out front. I mean, this is just like having a negative 1, so you'll just have it out front. So then you'll have the 2x squared over x squared plus 1 over the x squared. Okay, so here the x squares cancel, which leaves me with 2. And now go through and actually take the limit. So the limit as x approaches negative infinity of 3 would be 3. The limit with 2 divided by x as x approaches negative infinity would be 0. Again, that's just that property. So that your limit here would be 2, and your limit here would be 0. So you've got almost the same thing. It's just the fact that you've ended up with this negative out front. So a while ago you ended up with a positive 3 over square root 2, and this time you end up with negative 3 over square root 2. So that would indicate that you would also have two different asymptotes. As you go to the right to positive infinity, it approaches one asymptote. As it goes to the left to negative infinity, it approaches a different asymptote.